In this lesson, we dig into Lambda functions and powerful vectorized operations. Lambda functions and vectorized operations in Pandas. In this lesson, we dig into Lambda functions and powerful vectorized operations. Ever wondered how to apply custom calculations efficiently to your data? You will learn ways to write functions that run superfast over large tables without any loops. These skills help you wrangle, clean, and analyze data like a pro. Ready? Let us get started. Running the cell now. To practice, write down one thing you hope to learn today. Let us start by hiding warning messages so our output will not be noisy. We import the warnings library. Import numpy as np. We set the random seed to 42 for reproducibility. Now we tell Python to ignore all warnings for a cleaner workspace. Running the cell now. This cell sets up the environment by importing libraries and fixing the random seed for reproducibility with no visible output. It's a crucial first step for applying consistent Lambda functions and vectorized operations later in our lesson. Notice that warnings are also suppressed here to keep our output clean as we experiment. We need data for practice, so let us load a classic example. We show that these lines will set up the tips dataset. We import Seaborn, which has popular example sets for quick demos. We load tips, a small table about restaurant bills, tips, gender, and meal time. We show the shape to see how many rows and columns are present. We preview the very first rows to understand our data. Running the cell now. Here, we load the tips dataset and confirm its size with 244 rows and 7 columns, giving us a manageable but rich dataset to practice on. Notice the key columns like total_bill, tip, and size, which are perfect candidates for applying Lambda functions and vectorized operations to calculate custom metrics efficiently. This setup ensures we're working with real, relatable data for our coding exercises ahead. Try running this cell and look at the table so you get a feel for the columns. Before we dive in, let us see why these methods matter. Why use Lambda functions and vectorized operations? Pandas works best when you avoid loops. Vectorized code runs on whole columns at once. Lambda functions let you quickly write new calculations. They are key for clean, efficient data work. Running the cell now. Can you spot any column you would like to calculate with from the tips table? Let us start with a simple example, adding a new column using vectorized math. We add a new column called total. For each row, it is total_bill plus tip. Pandas handles this addition across all rows with just one line. This is vectorization. We print just the columns total_bill, tip, and total to check the result for the first few rows. Running the cell now. Here, the new total column is created by adding the total_bill and tip columns using vectorized addition, which efficiently operates on entire columns at once. Notice how each total value is the sum of the corresponding total_bill and tip, demonstrating a concise and fast way to perform column-wise calculations without loops. This highlights the power of vectorized operations combined with Lambda functions for quick, readable data transformations. Try thinking about other columns you could add, subtract, or multiply like this. Now let us use a condition to make a true or false column in one shot. We create a new column called big_tip. It is true when tip is greater than 5. This lets us quickly classify each row based on a condition. Printing helps us see which rows got marked as big tips. Running the cell now. This output shows a new column, big_tip, created using a vectorized condition that checks if each tip is greater than 5. Notice how big_tip is a Boolean column aligned with tip, indicating false for all these first 5 rows where tips are small. This demonstrates how Lambda or vectorized operations let you quickly generate meaningful new columns without looping. Next time you want to label or flag something, remember, try vectorization first. Let us define lambda functions before we use them. What are lambda functions? A lambda function is a short, one-line function. In Pandas, we often use lambdas inside apply. Syntax example, a lambda xx plus 5. Running the cell now. Think about a calculation you can write in a single line using a variable x. Let us use a lambda to double the tip column and store it. We add a new column tip underscore twice. We use the apply function with a lambda to double every tip value. Lambda lets us quickly define and use a small function in one step. Now, we print both tip and tip underscore twice side by side to check the math. Running the cell now. Here, the new column tip underscore twice shows each original tip value doubled, demonstrating how a lambda function can be used with apply to perform quick, element-wise operations on a Pandas series. Notice how the output maintains the same shape and row alignment as the original tip column, highlighting the efficiency of lambdas for concise data transformations. Practice, try changing the multiplier to 3, or add 5 instead. Lambdas are great for creating new labels based on conditions. We create a new column service underscore label. Using a lambda, if a tip is greater than 5 we label it as generous, otherwise as normal. Now we print several rows to confirm our new labels work as intended. Running the cell now. This output shows the result of applying a lambda function to the tip column, creating a new service underscore labeled column that categorizes tips as a generous or a normal. Notice that all tips here are labeled normal because none exceed the threshold of 5, highlighting how the lambda's conditional logic works row by row. This demonstrates how lambdas enable quick, custom transformations within Pandas apply. Try changing the cutoff amount to something else and see what happens. Sometimes you want to use several columns together. Use apply with axis equals 1 for row-wise calculation. We add a bill underscore ratio column. It shows the tip divided by the total bill for every row. Using axis equals 1 makes apply pass a whole row to the lambda each time. Printing a few values shows how tip compares to the bill for different cases. Running the cell now. This output shows a new column, bill underscore ratio, created by applying a lambda function row-wise to calculate the tip as a fraction of the total bill. Notice how the lambda inside apply axis equals 1 lets us easily combine values from multiple columns into a single result. This demonstrates the power of lambdas for concise, custom row-level calculations in Pandas. You could use this pattern for custom scores or other row-based formulas. Let us talk about performance and when to use these tools. Vectorized versus apply, which is faster? Vectorized math is much faster, runs in C under the hood. Apply and lambda are more flexible but slower for big data. Tip: prefer vectorized solutions when possible for speed. Running the cell now. Can you guess why built-in operations are so fast in Pandas? Vectorized operations are not just for numbers. You can use them on strings too. We make a new column tip underscore str by converting numbers to text and adding a $sign. This is a very fast operation done on the whole column at once. We print the two columns next to each other for a quick check. Running the cell now. The output shows the original numeric tip values alongside a new tip underscore str, a column where each tip is converted to a string with a appended using vectorized string operations. Notice how this adds the currency symbol efficiently to all rows without the need for slower apply functions. This demonstrates the lesson's point that vectorized methods are fast and concise for element-wise transformations. Try making a string column combining the day and time columns yourself. The map method is great for simple one-column function mapping. Here is another style you will see. We define a function named bonus. When size is at least 5, it returns 1, otherwise 0. This is the function definition for bonus, which checks if size is at least 5 and returns 1, otherwise 0. We use map to apply the bonus function to each value in the size column and create a new party_bonus column with the results. We print the first 6 rows of the size and party_bonus columns to preview the bonuses assigned. Running the cell now. This output shows how the .map function applies the bonus function element-wise to the size column, creating a new party_bonus column with 0 since all sizes are under 5. Notice the result is a simple binary flag per row, but this approach, while readable, can be slower on large data compared to fully vectorized operations. This example highlights the trade-off between flexibility with .map and performance in vectorized math. Did you notice map is often used with categoricals or scoring rules? This is a more advanced but super useful approach for vectorized conditional logic. This is a comment explaining that we use np.where for efficient conditional assignment. We import the NumPy library to use its array manipulation functions. We create a new column's meal_value in the data frame that labels each row as expensive if the total bill is over 30, otherwise standard. We display the first 7 rows of the data frame showing the total bill and the assigned meal value. Running the cell now. Here, we see the first 7 rows of the data frame with a new column's meal_value assigned via np.where, a vectorized conditional operation. Notice all total_bill values are under 30, so this meal_value is consistently a standard, demonstrating how np.where quickly applies conditions across the entire column without slow row-by-row loops, highlighting the efficiency of vectorized methods. Try writing your own rule for very cheap meals or luxury ones. Now let us combine techniques for a mini-project challenge. Mini-project, calculate tip percent and categorize. Challenge, create 2 new columns. 1. Tip_percent, tip divided by total_bill times 100, rounded to 1 decimal place. 2. Tip_level, use a lambda with apply to label as high if tip_percent at least 20, else normal. Ready? Let us code this together. Running the cell now. Do not worry if it seems tricky. You can pause, re-watch, and rewind this part anytime. First, we create a tip% column using vector math and rounding. We compute tip_percent as tip divided by total_bill times 100 and then rounded. This creates a new column and shows vectorization with math and rounding. We print several rows to check if the numbers look right. Running the cell now. This output shows the new tip_percent column, which calculates the tip as a percentage of the total bill, rounded to 1 decimal place. Notice how the values vary widely, with some tips like index 6 exceeding 20%, which will be important for categorizing tip levels in the next step. This confirms the vectorized calculation is working correctly before applying the lambda function to label tips as high or normal. Try changing .round 1 to no rounding and notice the difference. Now we use lambda to turn tip_percent into a high versus normal label. We add tip_level using apply with a lambda function. Any tip at least 20% is high, otherwise normal. We print out the percentage and level side by side for a few cases. Running the cell now. This output shows the first 10 rows of the new columns, tip_percent and the corresponding tip_level labels. Notice how tips with a %20 or above are categorized as a high, while others are a normal, demonstrating that the lambda function in apply correctly classifies each row based on tip generosity. This confirms the success of our classification step in the mini project. Can you make a low-to label for tips under 10%? Real data has missing values. Let us test vectorized math with a missing tip. This comment explains that we will perform vectorized math operations while handling missing values. We create a copy of the data frame to avoid changing the original data. We assign a nan value to the tip column in the first row to simulate a missing value. We add 5 to the tip column, resulting in a new column. Missing values remain missing after the addition. We print the first 3 rows of the original and new columns to observe the effect of the operation. Running the cell now. Here we see how adding 5 to the tip column handles missing values, where a tip is nan. The result in tip _plus_ 5 is also nan, preserving the missing data. This confirms that vectorized math operations propagate nans rather than filling or ignoring them, which is important before calculating tip percentages in our mini-project. Remember to handle missing values before summary statistics or modeling. You often fix missing values before calculation. Filling is easy with Fillner. We clean missing values in the tip column by filling them with 0 before doing any calculations. We create a new column tip_filled where missing tips are replaced with 0. We add the filled tip amount to the total bill to get a new total called new_total. We print the first 4 rows of the columns in tip_filled, and new_total to verify the changes. Running the cell now. Here, the output shows how we handle missing tip values by filling them with 0 using .fillner, ensuring no nans in the new tip_filled column. This allows us to accurately compute the new_total by adding tip_filled to total_bill, which is critical before calculating tip_% to avoid errors or misleading results. Notice that the first row's original tip was nan, now replaced with 0, keeping the total consistent. What would happen if you filled missing tips with the mean value instead? Mistakes happen. Let us see some typical issues you might face. Troubleshooting common lambda and vectorization errors. Common issues. Forgetting axis = 1 for row-based apply. Mismatched data types. Using a string method on a numeric column. Not handling missing values. Pandas usually gives a helpful error message. Check column types or try df.info to debug. Running the cell now. Always read errors carefully and check the column types before fixing. Time for a practice challenge. Let us make a new feature showing if a tip beats the average. We calculate the mean tip value from the tip column. We mark each row as above_average_tip if the tip is greater than the mean. Display the computed mean for reference. We randomly preview a few rows to see the result. Sampling lets us get a nice variety of cases quickly. Running the cell now. The output shows a new Boolean column above_average_tip correctly marking whether each tip is above the average tip value of 3.00. Notice how the above_average_tip flags tips like 3.18 and 5.16 as true, while tips of 2.00 are false, demonstrating that vectorized comparison handles row-wise logic efficiently without needing apply. This confirms the code's intent to vectorize conditions, avoiding common pitfalls like missing axis = 1 or incorrect data types. Try changing random_state or tipping threshold for a different sample. If you are finding this valuable, hit like and tell us your favorite Lambda trick. Let us wrap up with a big picture summary of what you have learned. Recap: what did you learn? Lambda functions let you quickly apply logic to columns. Vectorized math is super fast and clean. Use apply axis 1 for row-based calculations with several columns. Handle missing values and check types to avoid bugs. Practice these skills with your own data for speed and clarity. Running the cell now. For extra practice, try creating your own custom columns using tips, day, and time together. Thanks for following along. One last tip before you go. Want more data skills? Subscribe and check out our next Pandas lesson on Group B tricks and real-world analysis. Thanks for learning with us. Running the cell now. Before you start another video, review your notes and comment below with a question or helpful tip.